Hi everyone, today I would like to talk about nonlinear least square. So this is an extension of linear least square. In the linear least square, we consider the normal ordinary least square, then we talk about multi-objective least square, then I talk about constraint least square. Now it's a time to talk about nonlinear least square, which happens a lot in practice, right? This is more common than ordinary least square. We usually approximate our problem to be like a linear least square, and we explain to you in this video how we achieved doing this. Okay, so now let's start. So let's first motivate what is a nonlinear least square and how we can formulate our problem like that. Okay, now assume you have n nonlinear equations and n unknowns. So this is very similar to the linear least square when I said that A is n by n, but here is a nonlinear system of equation. So we don't have any matrix A. Remember, when I talk about the linear transformation, that linear transformation can be explained by matrix vector product, right? When you're transforming a vector, right, it seems that you're multiplying by a linear matrix. But this one, there is no linear matrix here because it's a nonlinear equations. So assume you have m equations correspond to the m rows similar to that, and n unknowns, right? Each of these equation is like f of I of x equal to 0, where I is changing from 1 to n, right? So each of these f of I of x is nonlinear equation. Nonlinear equation. For example, this one can be x e to the x minus x equal to 0, for example, or minus x squared equal to 0. So that can be, for example, f1 of x, right? f2 of x can be, for example, I don't know, sine of x plus x cosine of x equal to 0. So like this. Okay, good. Which x, for example, can be n-dimensional, x1, x2, all the way to xn, right? So if you look at f of I of x, right, this function is from Rn because x is n-dimensional to R. So it's a scalar, this function, right? So f I of x, each one, so like this one is like a scalar function. The output is like it's a number, right? So it takes the input, let's say that n-dimensional vector. So x is this, x1, x2, all the way to xn, all right? And the output is gonna be like 5, 6, it's number. So it's like that, right? Now, so each fi of x. Now I'm gonna say that like a similar case to the linear least square. So what I'm gonna do to make sure that you understand this concept very well is going from nonlinear to linear back and forth to make sure that we map the concepts together. So what I'm doing here, I'm gonna put these functions, stack them together, right? So as a like a vector, as a m-dimensional vector, right? So remember we have m nonlinear equation. So I'm going to stack them together to have a vector of m by 1, right? A column vector. Similar to linear least square, right? In a linear least square, what did we have? In a linear least square, we had A1 transpose first. We had a matrix A, right? But how do you represent this matrix A? By its vector row representation, A1 transpose, A2 transpose, all the way to AM transpose, where this AI transpose are the rows of matrix A, right? So when you write this, this was matrix A, but in a sense, you could represent this least square, linear least square, the same way as what we are representing here as follows, right? We could represent it like this. A1 transpose X minus B1, A2 transpose X minus B2, all the way to AM transpose X minus BM. So this is equal to 0, right? So each line or each row corresponds to a linear system of equation, and that represents AX minus B, right? That represents AX minus B. That's exactly what we're doing, because this part, guess what? This one is nothing but AX, right? Which we write A as a row representation. So each of this is a linear equation, linear, or if you want to say affine, right? But now here, the same we apply the same concept in a nonlinear sense, but each of them is a nonlinear equation. So this f of I of x that we have, right? Now we stack them together. Now we have m because I was changing from 1 to m. So I have f1 of x, f2 of x, and all the way to fm of x. Now this function f of x, this one is from Rn because x is n-dimensional to Rm, right? Because we have a number for each of these. Number, right? We have m of this number, right? So it's very important to get the concept, right? So f of x is from Rn to Rm, okay? Good. So similar to linear case, again, we have three different categorization. Depends on the dimension of this m and this m. If we have more nonlinear equation than number of unknowns, right? In a case that m is greater than n, we call it overdetermined system of equation. More equation than unknown. If m is equal to n, this is a square, right? Same number of equation as number of unknowns. If m is less than n, we have underdetermined system of equation. Less equation, less nonlinear equation in this case than unknown, similar to the linear case. So up to now, we successfully mapped the linear and nonlinear case together. Okay, very good. Now let's talk about the least square approximation for the nonlinear case. Again, let's motivate them. Let's talk about the linear case still to make sure that we motivate this nonlinear case better. You see, in linear least square, what we do, we are trying to minimize this quantity, ax minus b square, right? Okay, because what we say usually is that the equation ax equal to b, right, does not really have a solution, or we cannot really find a solution for this, right? What we're gonna do, we're gonna find this quantity ax minus b and minimize this norm, right? It's like a residual. We're gonna try to minimize the distance from ax and b. So ax is a vector and b is a vector. We want to find the x such that the distance between ax and b in terms of a Euclidean distance is minimized. That's what we want to do. I want to do the same thing for nonlinear case, right? So what is the ax minus b here? What is ax minus b? I talk about that. This is ax minus b here. The ax minus b is f of x. So I want to minimize norm of f of x square. That's my goal, right? Well, what is norm of x squared? Remember, f of x is a vector, right? What is the norm of x? Note if a is a1, a2, all the way to an, norm of a squared is nothing but sum of square of each component, I from 1 to n, right? The same thing is here. Each component of f of x is what? f1 of x squared, f2 of x, all the way to fm of x squared, right? This corresponds to this component. Good. So I want to minimize this. It's still very easy after we map it to the linear case, right? So still we don't really have much new concept here. Okay. Now, when we cannot exactly find the solution, we want to minimize this. That's what I said here. Good. Okay. So what is the way to do this, like a linear case? How do we do this? Like in what we learn in calculus, always you take a derivative with respect to the x and you set it to 0. That's what we do, right? Okay, so one thing that it's important to remind you is that this norm is a scalar quantity. F of x is m-dimensional, right? Remember, we stack the vectors. But the norm of f of x squared is a scalar quantity, right? So I want the gradient of f of x. Remember, gradient of f of x. When f of x is a scalar quantity, gradient would be a column vector, and it was defined as follows, right? The derivative of f of x respect to each component, and that's why it's a column vector. Is always has the same dimension as the x, as the argument inside x, right? So f of x, x2, all the way to f of x, xn, right? So we want the gradient of f of x to be 0. Let's do this one. So I write this gradient of f of normal f of x squared to be 0, right? I want this gradient to be 0. So that was a note that I had, was the definition of gradient. But we want this one to be 0, right? With respect to each xi, when you put them in a column vector format, you get this one. Okay, let's take a gradient. So what we write the definition of a normal f of x squared. We write this sum of I from 1 to m, f of I of x squared. This is this. This is this. That's what this one says. Okay, we take a gradient, and what do we get? Properties of the derivative. Okay, what's the derivative of xa respect to x is a xa minus 1. So here 2 comes here, right? 2 comes here, and then we have fi of x, right? And then gradient of fi of x, like a chain rule that we have. Okay, good. So now if you want this one to be 0, equal to 0, right? But if you put them in a vector and matrix notation, this one you can write it as follows as well. This one you can write it as follows as well. This quantity become like this: 2d f of x transpose times f of x. What is d? D is a derivative matrix or Jacobian matrix. Remember we talked about that in terms of affine and linear transformation, right? D is a derivative or Jacobian matrix, right? Which is m by n. M was a number of equation, n was a number of unknown, right? So this very important condition that I have here, we call it the optimality condition. More about that right now. We'll talk about that right now. But before this, I want to make sure that everybody actually is familiar with this concept. This derivative or Jacobian notation, Jacobian matrix, I talk about in one of the video. I make sure to put a link to them in the description to that video. Definitely check that out. It's pretty important, and we use it extensively for the nonlinear least square, right? But in a sense, if x hat is a minimizer of a nonlinear equation, then we want this optimality condition to hold. It's a necessary condition. It's not sufficient, right? It's a necessary condition. So if it's a x hat is a minimizer, we want this condition to hold. Okay. Now, are we talking about something new, or we already know about that? Have we used this one in the past for a linear case? Let's see. Let's see. When we have a linear case, let's map that. What is f of x? What is our f of x in linear case? A1 transpose x minus b1, A2 transpose x minus b2, all the way to AM transpose x minus bn. Okay, good. So that's our f of x, which is equal to what? Ax minus b. But what is d of f of x? What is d of f of x? Right? How would you define this? So perhaps it's good actually to define d of f of x. Let's see whether I can add a page here. It's gonna add a page here, no problems. I'm gonna write here actually. Yeah, let's go over this. So let's go over this D matrix here. Jacobian matrix. So remember, what is f of x? It's always a confusion for people. This df of x is gradient. This week later on we talk about the Hessian, right? So this f of x is a vector value now. It's not a scalar value. Gradient with f of x was a scalar value, f of m of x. So it's gonna become round of f of 1 of x, x1, round of f1 of x, x2, all the way round of f1 of x, xn, right? Here we can round off fm of x, x1, and all the way to round off fm of x, xn. You see, it's m by n. M rows correspond to each equation and n columns. So it's m by n. I would like to calculate this quantity here for the linear case, right? Let's see what is d of f of x in this case. So, right, so what is f of x that we have? Let's write it one more time. Is a1 transpose x minus b1, a2 transpose x minus b2, all the way to am transpose x minus bm. All right, so let's put it here. Let's see what we get. So f1 of x respect to x1. So guys, what is this quantity? What is this quantity here? I'm gonna put it here. What is this quantity? This one becomes a1 1 x1 plus a1 2 x2 all the way to a1 n xn minus b1, right? This is the first row. So if you take it with respect to x1, you get a1 1. If you take it with respect to x2, you get a1 2 all the way to a1 n. Same thing, if you do it for row 2, you get a2 1, a2 2 all the way to a2 n. Here you get am1 all the way to am n. What is this one? This is a. This is a. So df of x is actually a. Okay, good. Now that we know this one, let's go ahead and calculate this quantity here. I would like to calculate this optimality condition. Let me grab this one, click on copy. I'm gonna go ahead and paste here, and let's see what is the optimality condition for the linear case. This is gonna become 2, which is not important. We can drop the 2. df of x, which is a transpose, is a transpose ax minus b. Remember, f was ax minus b. Becomes 2a transpose ax minus 2a transpose b. Let's forget about the 2. It's become a transpose ax equal to a transpose b. And what is this? This is just a normal equation. This is a normal equation. So optimality condition is nothing new. We also know about optimality condition, right? We used it actually extensively in the past for a linear case. Optimality condition is nothing but a normal equation. Okay, good. Now, up to now, we successfully map every concept to each other, between linear and nonlinear. Okay, now let's talk about what happens when things go wrong here. So why do we study nonlinear case? Why do we say that it's hard? Because unlike linear least square, the nonlinear least square may or may not have any solution. It may have infinite many solutions. It might have multiple solutions. It was not like a least square solution. Is that okay? A has a linearly independent column, then put A transpose A, inverse A transpose B. That's a solution. That's it. No, not really. It may or may not have solution. It might have multiple solutions. That's one thing. The first thing. Another distinction, which is very important, is that there is no QR, there is no Cholesky, there is no LU factorization for a nonlinear case. So now that's where things are different from each other. Okay. So now let's see how we can solve the nonlinear least square problem. The first algorithm that is very widely used is a Gauss Newton. Right? It has some shortcoming. We'll talk about the shortcoming of Gauss Newton algorithm. But first, let's talk about this Gauss Newton method. First, it's an iterative algorithm that generates sequence of points. We call it estimates, right? You start from initial point, you get another point, you start from x1, you get x2, you start then x2, they get x3, and we are hoping as the algorithm proceed, as we move forward, our new estimate is better estimate, or at least is closer to the solution we want in some sense that we're going to define, right? Okay, so here I define the d of f of x again. But here, sorry, it's a new page that I created, right? So I have to create a new page actually before that. But so this is a Gauss Newton algorithm, and all right. So let me just tell you what is this algorithm. So you start from some estimate x1, right? So here assume the generic x of k for the correspond to the kth iteration, and you keep doing this update, which we're gonna talk about that, until when this norm of this or norm square of this is a small f of x of k, right? Norm of f of x of k. Remember what's the equation we are trying to solve, right? The equation we are trying to solve is this. We are hoping to solve this equation. So we want this x of k to be a good estimate of this x, right? It's good estimate, right? Whenever this norm of f of x of k is a small, we know that we are converging, right? How do we know it's a small? For example, you can do some sort of, we talk about the stopping condition, of course, less than epsilon, right? In that case, for example, you know that you have to terminate the algorithm.